All right, so welcome to our fifth session. We're one session behind here, but we're going to catch up tomorrow. You're welcome to join in person tomorrow, same time, 6 to 9, or you can just catch the recording afterwards. Either way is just fine. So I'm going to share my screen. Okay, let's start with our class agenda we usually look at. So here we are in session 5, and okay, I just forgot to change the title here. We're not talking about regression metrics. We are talking about multi-class classification metrics. And let's skip this for today. I have your assignment 2 about halfway written. So I just need to finish the last piece of that. I'll have that ready for you to start on tomorrow. Then we'll push that deadline out just a little bit. So don't worry about having that all done and complete by Wednesday of next week. I'll publish that in the official timeline of that. So we spent a lot of time talking about binary classification, looking at 0 and 1. Last time we met, we talked about regression classification. So if you have a numerical scalar variable that can take on a range of values. Today, we're going to visit a slightly more complex topic in classification problems. So we're going back to classification, but we're not just going to talk about binary classification. We're going to talk about something called multi-class classification. So what if you're not just predicting, is it a banana or is it not a banana? You're actually interested in predicting, is it an apple or a banana or a pear? So these are multiple class options. We're just going to touch on confusion matrix, which you guys have looked at before, but maybe we're going to spend a little more time interpreting it with our new kind of understanding of this world of metrics. We're going to look at all the metrics that we've already looked at before. Sorry, so many typos in here. We'll do a break after recall. So we're going to look at the same metrics we've looked at before: precision, accuracy, recall, F1. But now we're going to look at it from this new lens of multi-class classification, not just the binary classification case. We're going to touch on probably one of the most mathematically deep topics we'll get into in this class will be categorical cross entropy, which is used a lot in neural networks, but you already have a really strong foundation for this with log loss. So this is just a very small extension on a topic that you're already familiar with from binary classification. And then I feel like I'd be remiss if I didn't mention just the different ways you can set up the problem in terms of defining your target variable, one versus all, one versus one. And then there's also this other topic called multi-label classification. So not to be confused with multi-class labels, multi-label classification. So we'll just touch on that. Here's where we're at in the course. So we've gone through 1, 2, 3, and 4. We're now at session 5. By tomorrow, we'll be at 6, and then we're going to finish out with 7 and 8. And I actually did combine these, so there's not 9 topics. There's 8. All right, let's jump in. Okay, so we're going to talk about multi-class classification. We're just going to reorient on what that is since we stepped away from this for a while and we're jumping back between classification and regression. And then we're going to talk about the various metrics for how you would calculate those for multiple classes. So accuracy, confusion matrices, macro, micro weighted averages for precision, recall, F1 score. Then we're going to talk about categorical cross-entropy and ending with one versus all, one versus one, and that multi-label classification. Okay, so multi-class classification is a type of problem where the goal is to classify the instances into 3 or more categories. I say 3 or more because if it's 2 categories, it's binary classification. This is what we've spent a lot of this class and the previous class talking about. Is it an apple or is it any other fruit that is not an apple? This is what we've spent a lot of time talking about, but this is binary classification, which involves distinguishing between 2 classes. Is it spam or is it not spam? Multi-class classification deals with the scenario where there's more than 2 possible outcomes. So this is just 2 outcomes. It's either class 1 or class 0, 1 or 2. In multi-class classification, it can be an apple, or it can be a pear, or it can be a banana, or it can be an orange. So there's a lot of different labels. It can be any one of those situations. So when we say multi-class classification, we already talked about this, but that's what we're talking about. Here's an example you've already worked with. So you spent a lot of time building your iris data set, your iris model in the last class. This is a multi-class classification problem because it can either be setosa, it can either be versicolor or virginica. So it can be one of these 3. Note for all of this class until we get to the very end, it can be one of these classes, but it cannot be 2 of these classes, or it cannot be 3 of these classes. So it is either iris setosa or it's not. It's either iris versicolor or it's not. It's either virginica or it's not. It cannot be both virginica and setosa at the same time. That's how we're going to use this terminology, multi-class label. So the thing to remember when you're working with multi-class classification problems is that you can encounter really imbalanced class distributions where one category might have a very small representation compared to other categories. So especially if you start to build out more and more categories. So we looked at it's just an example of that. So what that means, say we've got these 3 things that we're trying to predict. Perhaps this is 80% of our data set. This is 15%, and maybe this only represents 5% of our data set. We just don't have a lot of representation of this 3rd class. So you have to be kind of conscious of that. An example of that is when we looked at that image data set that was trying to classify these different land situations. We had pictures of highways, we had pictures of farms and fields, and so all these images. And some images had a higher population than other images. There were a few images categories and a few image labels that only had a really small representation. And that's because we had 10 different classes. So these multi-class classification problems, while we showed kind of the minimum example for that, which is just 3 classes, they can actually have quite a few classes. You have to investigate each class, see what the representation of that is. And maybe you might even have to handle that class imbalance using the oversampling, undersampling, all the techniques that we talked about in the previous class to make sure that it performs well against all the classes. It's not biased towards one category or another. So many of the algorithms, the nice thing about multi-class classification, many of the algorithms that we've already talked about, they just extend to this. So, logistic regression isn't just for binary classification, or decision trees aren't specifically for that. They often have methods and functions built into them for us to use these multi-class metrics and really just extend the model and the application to the multi-class domain. So it's just a slight expansion. All right, so let's look at a few metrics. We're going to look at accuracy, precision, recall, and F1, and also the confusion matrix. So multi-class accuracy, how would, in that multi-class paradigm, how would we calculate accuracy? We know that accuracy is a measure of the proportion of correctly classified instances. How many times did we correctly predict the instance, predict the y variable, out of all of the predictions that we made? So it's a very general assessment of how the model performs across all of the classes. So in multi-class classification, it's a pretty straightforward calculation. If we have our 3 classes, we have our, flower 1, flower 2, flower 3. How many times did we predict flower 1 correctly? Oh, 5 times. Okay. Plus, how many times did we predict flower 2 correctly? 10 times. Okay. Add those together. Now we're at 15. How many times did we predict flower 3 correctly? Another 5 times. Great. Add that together. Now we're at 20. How many predictions did we make overall? We made 40 predictions. Okay, we have an accuracy of 50%. So pretty straightforward with multi-class. You already know the interpretation for accuracy. You want higher performance. We're trying to maximize accuracy, not minimize it. It's a commonly used metric for evaluating classification metrics or classification models in general and multi-class classification models. But for multi-class, we have to keep in mind that the weighting it's going to apply is it's going to treat everything equally. And so if we have that really small underrepresented class for a really small class imbalance class, us getting that wrong isn't a stronger or a more severe penalty in terms of accuracy. It's treated very equally. The results are treated equally among kind of all classes. So that's the downside. And there's no penalty applied to certain types of misclassification. So if you think about maybe predicting false negatives has the same weight as predicting a false positive, but maybe in your use case, that's not actually true. If you're maybe working with a medical use case, maybe there's a different weight or different severity or different impact to those things. So accuracy treats everything equally, both prediction errors and classes, which may be applicable to your use case, but it's worth thinking about. All right, we're going to do our traditional exercise. So let's just consider this example. We've got 100 fruits. We've got apples, oranges, and bananas, and they're pictures, images of fruits, and we're trying to classify them. So we train a model, and we evaluate the accuracy. It predicts 35 out of 40 apple images correctly. Oh, there we go. Correctly predicts. It correctly predicts 35 out of 40 apple images, 25 out of 30 orange images, and 28 out of 30 banana images. So for this problem, what is the accuracy? I'm just making sure that adds up. Okay, it does. Spend just a couple minutes on this. Okay, just want to make sure we were all in. All right, was anybody able to calculate the accuracy?
Yeah, overall it's 88%, right?
It is 88%. So this is fairly straightforward. We're just starting with what we know and what we're familiar with here, which is we're adding up all the instances in which we were correct. So 35, 25, 28. and all the instances in which we made a prediction, whether we were correct or not. And that was 100. It's going to be all of our instances. So 88 over 100, 88%. Okay, let's take a minute to think about confusion matrix. I should have put maybe the first slide of this should have been just a binary classification confusion matrix. But imagine just these top 4 squares here. We've got our true positives, the situations where we actually predicted one, and in reality, the ground truth, our y actually was 1. We've got situations where we predicted 2, or predicted 0 if we're thinking binary classification, and it actually was 0 binary classification. So those would be our true negatives. And then we're going to have the 2 situations where we got those wrong. Predicted 1, but it was supposed to be 2. Predicted 2, but it was supposed to be 1. So this is what we've been using, what we've been working with, just kind of in those 4 squares, our TP, TN, FP, FN numbers. Expanding that out, we're going to push that out to what if we had 4 classes? So instead of 0 and 1, now we have 1, 2, 3, 4. You would read this very much the same way. Down this diagonal line, this is what we got correct. These are our true positive predictions. You can think of it that way, but true label predictions maybe. Because instead of having positive and negative, 0 and 1, now we just have classes. We predicted 1 and it was 1. We predicted 2 and it was 2. We predicted 3 and it was 3, and we predicted 4 and it was 4. But sometimes we're going to predict 1 and it's not going to be 1. It's going the true answer was actually 2, or the true answer was 3, or the true answer was 4. Or on the flip side, if you want to read down, if you want to read a column at a time, when our ground truth label is 2, how is our model making that prediction? Is it mostly predicting, where is it getting that right? Where is it getting that wrong? So this is how you would read a confusion matrix. I want to pause on here for a second. Any questions? Okay, we're gonna jump to this slide here. So when you actually print these out, this is maybe what it might look like across an even larger set of predicted labels and true labels. And you're going to get some type of grading, some type of coloring for how correct you are, or how often that's, correct or off. And this one's obviously quite good, probably very overfit to the data set, but it can start to give you insight into, am I more often misclassifying t-shirts as shorts, or am I more often misclassifying t-shirts as dresses? Or when I'm trying to predict something as a dress, what are the things that I'm getting most confused with about that? What about it is confusing the model? It can help with refinement. Okay, that's all I wanted to say, because we're going to use a confusion matrix a little later. I'm going to have you guys run your calculations off of that. Because if you remember, to calculate precision and recall, all you need is a confusion matrix to do that, and F1 actually, to calculate precision, recall, and F1. You don't actually need the Y true and the Y hat. You can just do that with with a confusion matrix. Okay. Precision and recall, macro, micro, weighted averages. How would you calculate precision for a multi-class problem where you can have apple or banana or pear? So precision in the context of multi-class classification, we can measure it for each class. So that traditional binary classification that we've been talking about for precision, you can apply that to each class. So out of all the instances predicted as belonging to a particular class, how many actually belong to that class? So we can think about, for a banana, what was the precision of the banana class? For an apple, what was the precision of the apple class? Maybe I should go to the next slide, this slide. The precision for a given class is the fraction of all instances. You guys know the precision formula. It's all the true positives over the true positives plus the false positives. If we do that for each class, so precision at class A is the true positives for class A over the true positives for class A over the false positives for class A. So it's not going to be the entire data set. It is specific to class A or specific to banana. So you'd measure this for each class. That's precision by class. Here's an example. Let's actually look at something. Let's measure the model's ability to identify the instances of these particular classes. So class 1 is it an urgent email, a normal email, or a spam email? So we just expanded our spam problem. We had a binary classification. It was spam or it wasn't spam. And now we want to know, is it spam, normal, or urgent? So we added a third class there. So we would create this confusion matrix that we had talked about, this binary confusion matrix for each class. And from that confusion matrix, we can calculate the precision for each class. So this first class has a precision of 0.42, this normal class 0.52, spam has a precision of 0.86. So now we have a model that's a multi-class classification model that's classifying class 1, class 2, class 3, but now we have 3 performance metrics across all of these. So a natural question might be, how do we calculate precision across all of the groups? So I'm going to ask you guys here in a second if you have any thoughts on that. But first, I'm going to touch on recall too, because it's kind of worth talking about both of these in the same context. We don't really need to repeat the same content twice because we're going to apply the same logic to both. So just touching back on recall. So in multi-class classification, recall is our sensitivity or our true positive rate, and it's the ability for the model to correctly identify instances of that class out of all instances that truly belong to that class. So out of everything that exists in the data set, how many did we recall? How many did we collect? This is our formula, and same thing. This is recall by class. So you have to calculate this. If you have 10 classes, you're going to have 10 recall metrics for recall by class. So it's a fraction of true positives over true positives plus false negatives, all in respect to that specific class. So for precision or recall, how might we calculate these? How might we use this to create a metric that aggregates across these classes? Anybody have any thoughts?
Could you end up with 2 calculations, one for the specific class that it matched and one overall? Or
I think you could. Explain more.
Yeah, so I'm thinking that if you took and you looked at, let's say we're doing 3 different variations of it, right? Apple, orange, pear. And you wanted to see how it matched overall for the whole grouping of all 3, but then you wanted to look at just pear and the accuracy or the precision for just pear. I think that if you looked at the precision for all 3, it should somehow end up being 100%, but maybe it's not accurate where something was put into the pear group, it should be in the apple group or something. Hope that makes sense.
I think it does, and I think you're on the right track, which we're gonna we're going to talk, you're hitting something really important, which is how do we weight these different classes? And when mistakes are made in one class, but we're really good at everything else, how does our metric take that into consideration? That's really important. All right, so we're going to look at 3 ways to do this. One is a macro average, one is a micro average, and what is a weighted average. So these are just averages. You might think of a way we could do this. How can we get one model metric? We want to compare model 1 to 2 to 3 to n. So how can we get one metric instead of 10 metrics, even when we have 10 classes? One metric per model. We could, there's 3 values here. We could just add these up and divide them by 3. So it's 0.42 plus 0.52 plus 0.86. And then let's just divide them by 3. What's the average precision? Sometimes this is called average precision. We're going to call that macro averaged precision because there's kind of 2 types of average precision. So I don't want to confuse too much. We're going to talk about the specific ways. So in macro average precision, we're going to do exactly that. We're going to calculate for each class. So this is important. This is separate for each class. We're going to calculate true positives, false negatives, true negatives, all the things that we need. We don't actually need true negatives for precision. That's why that's not in here. But then we're going to compute precision and recall for each class, just like we did in this picture for, I had to sneeze, I'm sorry. One moment. Back. Okay. So just like we did in this picture, we calculated the precision for each class. We would do the same thing for recall. That's why I said we're going to talk about both of them. Doesn't really make sense to separate them out because it's the same approach. So we'd compute either the precision or the recall or both for each class using our formula. And then we're going to average them. So we're just going to add them all up and divide by the number of classes. So add the precision and the recall you calculated for each class, divide by n. Here's a picture, probably better describes that than I just did. So precision, macro average precision. We had the precision for each class, precision for banana, precision for, and I think this is what you were saying. I think this is exactly what you were saying, is precision for banana, precision for pear, precision up to n, and then we divide them by n. How many classes?
That's what I was trying to say.
That's what I thought. Yeah, you were right on it. And we do the same for recall. So we're just replacing precision here with recall. Recall for class A, recall for class B, recall for class N, divide by n. So here's, if we have our confusion matrix here, the way that you can slice this out is you can slice out the precision for each of these classes, the recall for each of these classes, and then you could even average these numbers to get your average, macro average precision and your macro average recall. Sorry, I have a terrible habit of using blurry photos. Okay, micro average precision. So that's one way. That's a very simple way. It's pretty straightforward. I think it's pretty intuitive. I guess I was just about to talk about the pros and cons, but we're going to get to that in a second. The micro average precision. So this is another way of calculating average. So we're still going to do the average, but in this case, we're going to calculate the true positives, false negatives across all of the classes. And we're going to sum those across all of the classes instead of calculating it individually. Let's look at what that looks like here. So instead of we pre-calculated precision for each of these, and we pre-calculated kind of recall. instead of doing it that way, we could just put true precision, the true precision of A plus true precision of B. So we're taking our formula for precision, which we had defined here. If you remember, it's TP over TP plus FP. What if we took the TP of class A plus the TP of class B plus the TP of class N and made that our numerator instead of, so we're kind of going back to the base formula for precision here. There we are. So now we have the true positive for all of our classes, and we're adding those up as the numerator. And then on the bottom, we have the true positive and the false positive, the TP and the FP, for each of our classes. And we're adding that up as the denominator. So this is also average precision. It's just a different way of calculating it. You can expand that to recall as well.
Emily,
Yeah.
the slide prior, it's supposed to be micro average precision and recall, not
Oh,
max, right? Am I right?
You. I am the.
No, you're fine. I just want to make sure that I didn't.
Yes.
Okay, thanks.
100%. I'll make sure I did that here. Yes. I'm gonna have a lot of typos in here, I feel like. So there is some slight differences between the macro and the micro averaging in how they aggregate those performance metrics. The macro averaging is really emphasizing the class performance. So the performance by category, like by banana or by apple. So it's equally weighting, it gives equal weight to each class. So an apple class is just as important as a banana class, which is just as important as a pear class. In micro averaging, we're weighting the instance. See, because we're passing the number of true positives and the number of false positives, we're saying that this image is just as important. Image 1 is just as important as image 2 is just as important as image 3 is just as important as image N. So there's a difference there. It comes into play with class imbalance problems. So if all of your classes are equally distributed, these metrics will give you the same value. If you have 33%, 33%, 33%, it doesn't, you can use either one. But if you have a class imbalance problem, if we have a situation where we only have 2 pictures of bananas and everything else is either an apple or a pear, in that case, if we use micro averaging, the second one here, and we say apply that metric, since each class has weight, we're averaging the weight by instance. I'm sorry, each instance has weight. We're averaging the weight by instance. Those 2 records of banana only have 2% weight, 2 out of 100. So there's 100 records. They only have 2% weight. So even if we get them wrong, that's not really going to impact the model that much. So that could be okay for your problem, or that could be a big problem. On the other hand, macro averaging is going to really unnecessarily weight that class, even though it makes up a small proportion of the data set. So you may get a really bad macro average because if you get just one of your bananas wrong, now you have a 50%, say accuracy. Let's just use accuracy here. You have 50% accuracy in a macro averaged world. That would have a huge penalty on your model performance because it's one of your 3 classes. It's a third of your performance. It counts as 33% of your performance. So it depends on your problem for which one that you might want to choose, whether you want to weight by class or by instance or record. Okay, maybe I have all the same stuff on this slide. So I guess these are summary slides. I should have said macro averaging summary. So treats each class equally. Each class has equal importance. It can be useful depending on your problem if you have an imbalanced data set and you want to ensure equal representation by each class. It can distort the perception of performance. Like I said, if you're performing very poorly on a very small proportion of the data set, it can really overly penalize that. So it can make your classifier look worse than it is, and it can disguise poor performance in some situations as well. Microaveraging, on the other hand, the impact here is overemphasizing that performance on the majority class, or the majority of the data, really, in general. Whatever the majority of your data, how it performs on the majority of your data is what it will represent. Maybe that's what you want. But also it can bias against classes with low representation. It can make it so that's not penalizing you for getting banana wrong 100% of the time, even if you never get a banana correct, if it's a very small proportion of overall population. Okay, this is why I brought up the confusion matrix. So here's a confusion matrix. I should maybe tell you your X and Y axis. Let's use the same one we had before. So let's say that your X-axis or your Y-axis is predicted, and your X-axis is the true outcome. So this is the true label, categories, and this is what you predicted. So you predicted A, and it was A. You predicted B, and it actually was A. You got that one wrong. You predicted C, and it was actually A. You predicted C, and it was actually B. You predicted A, and it was actually B. You predicted A, and it was actually C. Use this to calculate the macro average for precision and recall, and the micro average for precision and recall. Okay, let's spend 5 minutes on this. And I'm going to get water, so I will be back in 5. All right. Was anybody Was that enough time? Were you guys able to calculate that?
Not yet for me.
Okay, no worries. Take your time. All right. Anybody want to share what they were able to calculate for this? Do you guys get feedback, by the way? Do you hear anything in the background? No?
Yes.
You do. Okay.
Wrestling match going on there.
Great. Good to know. I apologize for that. It's good to know that is generally able to be heard in meetings as well. Funny. So I apologize for the noise. My husband's playing with my 1-year-old in the other room. Wrestling match is a good description. So for macro average, we're going to start with macro average precision. We're going to calculate the precision for class A, the precision for class B, and the precision for class C. And then we can macro average that precision by adding them together. So adding the precision for class A with precision for class B with precision for class 3 or class C, and then dividing them by 3 because there's 3 classes. to get our average precision, which will be somewhere in the middle of these three numbers. So to calculate precision for class A, it's how many did we get correct? Our true positives, which is 10, over our true positives plus, I want to make sure I say the correct thing here, plus our false negatives. Which one did we falsely predict as negative? 1 second. I apologize. Okay. So we'll see if they're quieter. So our false negatives. So we had 4 false negatives here. This was a predicted class B, but it was an actual A. Okay, so this was a false negative. We predicted class B, but it was actually an A. We predicted class C, but it was actually an A. So you can actually just sum this entire column. You can just sum by column. You take 10 plus 1 plus 3, and that's our denominator here. And then 10 is our numerator, because that's going to be the ones that we actually got correct here. Does that methodology make sense? This is just our regular precision calculation. It's just maybe reading the new version of the confusion matrix might be a little different. Okay. Yeah, is there a question?
So the real values are across are on the x-axis.
Yeah,
And the predicted values are on the y-axis.
I should have put a.
I did it backwards. That's the reason why I was thinking
Oh.
I was trying to get caught up here because I did it backwards. And so I was trying to change all my formulas around in my spreadsheet I'm creating.
I believe these are true. Sorry that these are backwards, or sorry that I didn't put these labels on here. That's me. My bad. And this was predicted y hat. Okay. Yes, this is how it should have been.
Okay.
It's definitely easy to mix up when I don't have labels on the axes. So your calculation should probably still be correct, John. Just flip the row and column.
Yeah. Okay, cool.
For recall, we can do the exact same thing. We're just going to flip what we're looking at. So we're going to take 10, and then we're going to sum recall across. So 10, and then we're going to grab 2 and 3. We're going to take 12, and we're going to grab 1 and 2. So see how precision sums, in this case, where we have predicted on the X and true on the Y, so it matters where your labels are. But in this case, our precision denominator sums column-wise, and our recall denominator sums row-wise. And then your numerator will always be what this diagonal axis here. So where A meets A, where B meets B, where C meets C. So there's a pattern you can use there if you want to just calculate the precision recall really fast from the confusion matrix. And then you would just average across those as well. 1 moment. This needs to get. Okay. So to calculate the micro average precision, we need the total number of true positives, false negatives. So notice the difference between the two ways that we calculated these. Remember, in this situation, we were looking at the precision given a class, macro level precision by class, and then we were averaging across those different values. Now, we're not looking at precision given a class. Now, for micro average, we're looking at what are the total number of true positives. So if we go back to our matrix, let's see, we have 10 true positives here, plus 12 true positives here, plus 15 here. So you sum the diagonal. The sum of the diagonal is the total number of true positives. So there's 37. Okay, now we also need to figure out how many false positives are there. How many times did we predict that something should have been of class? So a false positive, try to think of how to describe that in multi-class. So 2, 1, 3, 4, 2. So false positive, we predicted that this was a B, but it was actually an A. We predicted A, but it was actually a B. I have to think about that for a second. Those both sum to 15. Interesting. Let me get back to you on that. We have the same numbers for false positives and false negatives, which may be correct in the term of multi-class classification. But just working with these, if we have our numbers for these, we have 37 divided by 37 plus 15. It's about 0.711 for precision and 711 for recall. Those are going to be the same. So that's macro and micro. You might also ask yourself, is there a situation where we can, if we look at just this, we have precision and we have recall of class A, B, and C, and then we're just straight averaging them. So we're treating class A with 100% of the same weight as class B is the same weight as class C. But what if we wanted to weight one class or the other? Maybe because it's a larger percent of the population, for example. We did want to add a little bit of weight to that. Could we actually weight the performance of that class? We didn't want to just kind of throw it out the door altogether like we might do if we're looking kind of at that row level, but we wanted to weight the representation of that class so one class was more important than another. We won't do the calculation for this, but that's weighted averaging. And this takes into account the balance of the classes. So you can apply a weight based on the representation in the data set. So if we look at this micro average, say this is 80%, this is 10%, and this is 10%, we may take this number times 0.8, this number times 0.1, and this number times 0.1, and then divide by 3 to get a weighted average. So this has more important emphasis than the other two numbers. Okay, I know this can be kind of a deeper topic, so I added a link here that I pulled a lot of this material from, so it'll be familiar to everything that we talked about. So it's a good reference. They go into a little more detail too, and they have kind of some more visual pictures that you can use for reference. All right, let's go ahead and take a 10-minute break. So let's come back at 7:14 Central Time. All right, we are back. F1 score. So we talked about accuracy, precision, and recall applied to multi-class classification. And if you guys remember, there's an F beta score, and when beta is equal to 1, it becomes our F1 score, which is the harmonic mean between precision and recall. So how might we calculate F1 score for multi-class classification problems? Well, and if you remember our formula here for F1 is 2 times the precision times the recall over precision plus recall. Well, the easy answer is it's just the same. We have the same metrics types that we can look at for F1 score: macro averaged, micro averaged, and weighted. So all the concepts that we just talked about for precision and for recall also apply to F1 score, where the macro average we calculate the precision and the recall for each class and then plug that into this metric. Where in the micro average, we'd be calculating the actual predictions, the true positive, false negatives, and plugging that into this overall. So weighting the instances and not the classes. And then the weighted average is a situation where we can actually apply weight to the class based on the proportion of the proportion it represents in the data set. Okay, so let's try it out. Go ahead and download the notebook, the Jupyter multi-class classification metrics notebook. And in here, what you guys are going to do is apply precision score, which is a sklearn metrics class, recall score, and F1 score. And what you're going to do is you're going to apply macro averaged, micro averaged, and weighted averaged. I'm going to let you figure out how to do that, but I'll give you the hint that it is built into sklearn. So I set up some true labels and some predicted labels here. And notice that we're no longer working in binary classification. They're not zeros and ones. There's actually a 2 in here. So 0, 1, 2. There are 3 possible classes. So we predicted 0, it was actually 0. We predicted 2, it was actually 1. We predicted 1, it was actually 2, etc. I set up the first one for you. So a little bit of a hint in how to proceed with the other ones. You're going to go ahead and calculate. So this is the calculation of the, for each class. Yes, that's what this is the calculation for each class. So if we print this out. Around this. I gotta rerun the whole notebook. I apologize. Here. So this is the precision for class 0, the precision we had at class 0. This is the precision we had at class 1. This is the precision that we had for class 2. So this is the precision per class, the recall per class. So they're going to be an array of length n, where n is the number of classes that you have. It's a precision by class, the F1 score by class. What you're going to do is you're going to take these, well, not necessarily take these values, but you're going to find a way to represent these values as one metric for this, whatever our model was that generated these y-preds. So you're going to calculate macro averaged, calculate micro averaged, and calculate the weighted average. So here you'll do macro average, micro average, and weighted average for both precision, recall, and F1, or for all three of those, precision, recall, and F1. And then I put the names in here because if you just leave them the same, when you can just run this and it'll print them all out. So go ahead and give that a shot. Let's spend, I don't know, let's spend 15 minutes on this. Does that seem too long? I'll check in at 10 minutes. I'll check in at 7:30, but we'll plan on 7:34. All right, I want to check in. Were you guys able to figure out how to calculate some of these? Or are you still working on it?
I'm still working on mine.
No worries. We'll give you guys another 5 minutes here. Or 3 minutes. I'll check in at 7:34. Okay. Does anybody have some code they want to share for calculating the macro averaged precision recall in F1?
I dropped it in Slack.
In Slack. 1 moment. There we go. Perfect. I might have to sneeze. I'll go off camera here. Excellent. So to calculate the macro precision, just going to use this precision score method from sklearn, and we can look that up. We're just going to use precision score from sklearn, and we see that one of the values, one of the parameters that we can pass to this is an average, telling it how it's going to calculate that average. So if we look at our multi-class classification, we pass y true, y pred, and then to the average parameter, we're passing macro. So we're passing this value, macro, which calculates the metrics for each label and finds their unweighted mean. It's not a weighted mean. It does not take the imbalance into account. So they're letting us know how that macro metric works. Excuse me. It's a very straight average. So we're passing y true, y pred, and then we're passing average as macro. Excellent. Basically, we can do a really similar thing for all these other metrics. So we can call precision score, and now we can pass micro. We saw that that was an option, right? We looked here, sklearn, average. It can either take the values of micro, macro, samples, weighted, or binary. So it's either a binary one, or in micro, we calculate the metrics globally, the total number of true positives, false positives. So you don't have to do all that manually. sklearn will do that for you under the hood. So if we want to calculate the micro precision, we're going to pass this. Okay, now let's look at weighted precision. You just pass the value weighted, and then this situation, it calculates the metrics at each label, or at each label, but it finds their average weighted support, the number of true instances for each label. So it alters, it weights based on the imbalance of that class. Okay. So to do that one, for precision score, we would just do weighted. Like that's how they phrase it. Yeah, weighted. And you would apply that similar logic to recall an F1. So I'll let you guys do that, but I think you can figure out the pattern here. You could you just change the way that this is being averaged and use the same function, the same method from sklearn, which is really nice. And that's why we use sklearn, because it has all of these built-in tools for us to use that we don't really have to worry too much about, which is great. All right, any questions on that? Let's jump back into it. Okay. I still have MAE on here. That's so many typos. Categorical cross entropy. So categorical cross entropy, sometimes it's referred to as softmax cross entropy because it uses the natural log, the softmax, that sigmoid curve that we've talked about, or sometimes it's called multi-class log loss. And it's a log function commonly used in multi-class classification problems. Everything that we've talked about for multi-class classification up to this point has been based on the true label, but also the predicted value, the net predicted value. Did you predict a 1 or a 0? We haven't looked at the probability. And we know that there is value based on what we know about log loss as we looked at it in binary classification problems. We know that there is value in looking at the probability output and trying to come up with a metric that weights, that penalizes the model for making very confidently wrong predictions. And that's what categorical cross entropy does. It's really just an extension on our log loss metric. Do you guys remember that? Should I pull that back up? Maybe I should. Oh, session 4? I think so. No, it was binary. It was classification. Session 3. You can just look at this, I guess. No, must have been session 2. It was a while ago, so I think it is apt that we just take a brief look at it again. Okay, here, there we are. Recall that, remember, I guess I should say that recall's a metric. Remember that we talked about this log loss function where we had y at I times the log of p plus 1 minus y at I times the log of 1 minus p. And remember, we said when y is 1, that turns this segment on. Remember, and when we said when y is 1, 1 minus 1 is 0, and it turns this segment off. So when y is 1, we're taking the log of the probability, and when y is 0, we're taking the log of 1 minus the probability. So remember, that's what we kind of like talked about. When y is 1, it's the log of probability. When y is 0, it's log of 1 minus the probability. And then we calculate that for every instance, and then we summed over. Remember, we said this was just an average by n, and then we invert the sign. So we're going to get a negative out of here, so we're going to invert it so it's a positive value. Just wanted to bring that up. So this is the categorical cross entropy is going to be an extension on that. So keep that in mind. The formula for this is the L, the loss, is going to be negative I to C. C is the number of classes. So this is if you have 3 classes, it's to 3. If you have 4 classes, it's to 4. And it's y true at I times the log of y pred. Now this is really simplified. Why don't we have the minus, and when it's 1, we turn it on, and when it's another one, we turn it off? I have a video that I think, a video we're going to spend 5 minutes watching, that I think describes this really well. So we're going to calculate this overall loss is calculated as the average losses for all of the instances in the data set. The categorical cross entropy, it's going to use the probability of the true distribution, that one-hot encoded vector. You have, is it a banana or is it not a banana? Is it an apple or is it not an apple? Is it a pear or is it not a pear? So, in our multi-class problem, we can either have things labeled 1, 2, 3, or we can turn that. Remember one-hot encoding from the previous section? We can take something like 1, 2, 3, and we can say, is it 1 or is it not 1? And it's a series of 1s and 0s. Is it 2 or is it not 2? It's a series of 1s and 0s. Is it 3 or is it not 3? It's a series of 1s and 0s. There's a distribution in there, a distribution of 1s for apple, a distribution of 1s for banana. Is our predicted probability distribution similar to the distribution output in that vector? So basically, it's going to work really similar because it is an extension. And I have quite a few resources for this because I know this is a little bit of a heavier topic. It penalizes, it works the same as our log loss function. The model is going to penalize more heavily for confidently incorrect predictions. So let's think about what that means. When we said binary classification, in the binary classification sense, we said if you predict really confidently it's not a banana, but it's actually a banana, and that extends to the multi-class classification world. So if the true class is 1, it is spam, but your model predicts class 2, I think it's highly important mail. You've got whatever those 3 classes we had at the beginning slides were. But if it predicts highly confidently that it's class 2, then the log loss will be high for that. So this has a lot of relevancy in neural networks. So this is used quite a bit for neural network training to make sure that the neural network is approaching like a reasonable metric value, and it encourages high probabilities for the actual true class and low probabilities for other class. So that ends up leading to the accurate predictions. Okay, let's watch. I think I already have this pulled up. Let's watch 5 minutes of this video. I think it will be valuable. You guys are going to have to tell me if you can hear the sound or if I have to do something specific. Can you hear that sound?
No.
Okay, I figured that would be the case. Give me just one moment. I didn't think about this till just now. Not exactly sure. Maybe it's in the presenting settings. One moment. Yes, got it. I just had to switch to the tab. Okay.
A long, long way away
Can you hear it now? If I
from me. True.
You can?
Yep.
Okay, excellent.
If you made a neural network on the surface of Mars, you'd be a long, long way away from me. That's the truth. StatQuest. Hello, I'm Josh Starmer, and welcome to StatQuest. Today we're going to talk about Neural Networks Part 6, Cross-Entropy. Note, this StatQuest assumes that you already understand the main ideas behind neural networks, the main ideas behind backpropagation, and softmax and argmax. If not, check out the quests. The links are in the description below. Now, before we get started with cross-entropy, let me remind you that in the StatQuest on backpropagation main ideas, we had a simple neural network with a single output that, in theory, could give us any output value. In cases like this, we commonly use the sum of the squared residuals to determine how well the neural network fits the data.
We talked about that, some of the squared residuals in this class.
When I found this out, it felt wrong to keep it from you. DataCamp has a premium student plan for students in...
Bam. Now, when we have a neural network with multiple output values, we often run the data through argmax to make the output easy to interpret. But because argmax has a terrible derivative, we can't use it for backpropagation. So, in order to train the neural network, we use the softmax function. And the softmax output values are predicted probabilities between 0 and 1. And when the output is restricted to values between 0 and 1, we often use something called cross-entropy to determine how well the neural network fits the data. Cross-entropy is one of those things that sounds super fancy and complicated, but when it comes to neural networks, is super simple. To see how super simple it is, let's start with this super simple training dataset that has petal and sepal widths for known or observed iris species. Now let's plug in the petal and sepal widths for the first observed species, Setosa, and run the numbers through the neural network, and run the raw output values through the softmax function. Beep, beep, boop, beep, boop, boop, beep. Now, because we know the data are from Setosa, the cross entropy is the negative log, base E, of the softmax output value for Setosa, 0.57. In other words, we plug the predicted probability for the observed species into the cross entropy function. Note, if you have seen the cross entropy function before, this version may look different to you. The difference is because neural networks only need a simplified form of this general equation. In this summation, m is the number of output classes. In this case, m equals 3 because we have 3 output classes: Setosa, versicolor, and virginica. Thus, if we expanded the summation, we would get 1 term for Setosa, 1 term for versicolor, and 1 term for virginica. Now, because we know that the data from the first row comes from Setosa, the observed probability that the data comes from Setosa is 1, and the observed probabilities that the data came from versicolor and virginica are both 0.
Okay, so in our formula here, we had I from 1 to C, so the number of classes, y true times log y preda I. That's what they have here too. -1 times the log, natural log, of the predicted value at Setosa. What they're saying here is, because we're only interested in this cross entropy of Setosa, the other values are 1. This is 1, and the other ones are 0. The actual label under the hood, we know that the true label, the y true, is 1. These other 2 are 0, so in a sense, they get turned off. You can think about it in that sense. We talked about turning things on or turning things off, so in this situation, that gets turned off.
And that means the terms for versicolor and virginica go away. Poof. And we are left with -1 times the log of the predicted probability for Setosa. Anyway, going back to where we plugged in the predicted probability for Setosa, when we do the math, we get 0.56. Bam! So let's add the predicted probability for Setosa to the table, and the corresponding cross entropy value. Now let's plug in.
So here, let's try to go back just a second. Here we go. The cross entropy at Setosa, there we go, is the negative natural log of the predicted probability. So 0.57, which gives us 0.56. So that's how they calculated the cross entropy.
P-value. Now let's plug in the petal and sepal widths for the second observed species, virginica, and run the numbers through the neural network, and run the raw output values through the softmax function. Now, because we know the data are from virginica, we plug the predicted probability for virginica, 0.58, into the cross entropy equation. And the cross entropy value for virginica, the second row in the training data, is 0.54.
How to get the most of Grammarly free.
It's Kayla on behalf of Grammarly.
Likewise, we plug in the measurements on the third row, run the numbers through the neural network and softmax, and because we know the data are from versicolor, we plug the predicted probability for versicolor, 0.52, into the cross entropy equation. And the cross entropy for versicolor is 0.65. Now, to get the total error for the neural network, all we do is add up the cross entropy values. In this case, we get 1.75 as the total error. And we can use backpropagation to adjust.
I think that's good. Okay, so I linked that in the slides. If you guys want to watch more. Oh, you know what? Stop sharing my screen, didn't I?
So it's basically doing the same thing we were doing. by ignoring what it isn't, by the predicted, only looking at the predicted one. It's basically doing the treat this one as one, and the other is a zero.
Exactly. That's exactly right. So if the true label under the hood is 1, then let's look at the predicted probability for that label. I don't really care about what you predicted for the other labels. I wish I had a little whiteboard. This would actually be a good opportunity to whiteboard. But so if we have a predicted probability of 0.2 for the label I'm interested in, that is the log. That's what I'm going to take the log of. It's basically assuming that 0.8 is the probability that you predicted for everything else, that it isn't that class. But this metric doesn't really care whether you predicted it was a pear or was an apple when you're actually looking at a banana, if that makes sense.
Yeah.
Okay. Where were we? We were here. Okay, I have extra sources for you guys if you're interested. So feel free to check these out and continue to explore on your own as well. Let's see if those opened. My internet's being slow, but there's some extra resources on cross entropy loss that goes into it and walks through it in really simple examples. So if you want to kind of break that down a little more, talks about calculating the this is the formula we're more familiar with, calculating this for each one, and then how that would apply to cross entropy, how that's different from binary cross entropy, this formula we've been working with in the past, and has specific examples. Okay, I think it is, we are right on track today. It is break time. Let's take 10 minutes. Let's come back at 8:08. And we're back. Rounding out our session today, one versus all, one versus one strategies. And I recognize this is maybe a little backwards, tagging this on at the end. We could have thought about it in the beginning, but these are approaches for how you might represent your target variable in the multi-class classification. So in one versus all, or OVA, one hot encoding, this is kind of what we have been talking about. This is when we talk about all these multi-class classification metrics, when we were going through this log formula and we were saying 1 if it was this class, 0 if it was pretty much anything else. When we were calculating our precision and our recall for all of our different classes, we were using this approach. One versus all, OVA, or is it OVR? It's also called one versus rest. That's really common too, almost maybe more common than one versus all. In this situation, we might train K binary classifiers. That's a approach. There's also algorithms under the hood that just handle this type of classification, but let's think about it in this dynamic. Let's think about training 3 different random forest classifiers. We have our first random forest binary classifier, where if it's an airplane, it's a 1, and everything else is represented as a 0. It doesn't matter if it's a truck or a boat. Those are both zeros. They're treated the same to this classifier. We have another random forest binary classifier that is a truck is 1, and everything else is the same. It's an airplane or it's a ship. Those are both zeros in that case. And we have another third binary classifier. So we have a ship, and everything else is a 0. We have a truck and a plane. So I've actually used this approach before in the situation where we had these documents, and these documents could have comments on them made by people, and we wanted to understand if somebody made a comment, which one of the 9 downstream teams needed to take action on it. Is it legal? Is it sales? Is it HR? Who needs to do something to that contract who needs to take action? And so we trained 9 different classifiers. We said, what is the probability that HR needs to take action on this based on the comment? What is the probability that sales needs to take action on this based on the comment? So that is the one versus rest, or one versus all. You might think about this if we have, k-means clustering, for example, or any type of clustering. We have these 3 different groups. Maybe we've got 3 different classes. We've got a green class of triangles, a blue class of boxes, and a red class of X's. When in the strategy of one versus rest or one versus all, these would just in each model be broken down into 2 categories. You're either green or you're everybody else. You're either blue boxes or you're everybody else to the model. You're either red X's or you're everybody else to the model. And then if we wanted to make an inference, if we wanted to make a prediction on this data, what we would do is we would have a new unseen data point, and we don't know which class it is. We would pass it to each of these and see what the prediction it made, which one had the highest probability across all of these. Okay, so maybe this is saying exactly, I remember the piece I wanted to pull out of this. So from this data set, we can construct 3 binary classifiers. So going just one level deeper to our weights and our biases here. Remember, we had the y equals mx plus b. So the formula is different for each of these. Your B will be different, your starting point, your bias, but So the B over here is maybe that looks like 1. Maybe B over here is like 5. And maybe B over here is like, I don't know, if we kept following that up and eventually we get to the x-axis or the y-axis here, and maybe that's like 1,000. So your B's are different. Your M is also different. See, this is a very positive slope here. We've got an M, maybe M is 1, and this is a different slope. So maybe it's negative. So maybe M is like -1, and maybe M is like -10 here. It's really negative. So what I'm trying to say is your formula is going to be different. These are 3 different models. Okay. So the other approach to that is the 1 versus 1, where we train K times, I was planning on whiteboarding this, so you just had to bear with me, sorry. K times K minus 1 over 2 binary classifiers. So for each pair of classes. We'll come back to thinking about that here in a second. So contrasting to what we had before, we're saying if it's a plane, it's a 1. If it's anything else, it's a 0. We are not doing that in this case. In this case, it's a subset of the data. We're only looking at planes and ships. And for our first classifier, it's either a plane or it's a ship. And you have to pick one. It's either a plane or it's a truck. And you have to pick one. And it's a ship or it's a truck. So we're not considering all the other situations. So K times K minus 1 over 2. So we have 3 classes. Let's try to plug that in our, Let's try to plug that in our heads. So we have 3 classes here. K equals 3. So we have 3 minus 1. 3 minus 1 is 2. Times 3. 2 times 3 is 6. 6 divided by 2 is 3. So now we have 3. That's why we have 3 models for 3 classes. If we have 3 models, we have 3 classes. But maybe, I don't have a whiteboard, so maybe try plugging in some other numbers. Try 5. Don't try anything less than 3 because that would just be binary classification. It doesn't make sense. Maybe try 5. Try 10. Just try those numbers, see what you get, just play around with it, and then think about why that would be the case. Why you would have that many models mapped to those K classes. And if you think about it, the answer is going to be somewhere along the lines of you need a pair of each. So plane and boat, plane and truck, plane and if you added another class in here. Okay, so this is just a visual that might show different decision boundaries. So we just talked about 1 versus 1. So it either is green, it either is this green class or it's the blue class, or it is the red class or it's the blue class, or it is the red class, or in this line in the middle, I think, it is the red class or the green class. So I think this, you can read this decision boundary here, these 2 colors. This line is red and this one's green. So this is a 1 versus 1 of red to green. So if we have a decision boundary of 1 versus 1, this is what that decision boundary would look like for the red and the green class. For the green and the blue class, this is what the decision boundary would look like. So anything over here would get classified as blue for the 1 versus 1 strategy of the green and the blue class. And then this line here is the red class versus the blue class. So we have the red line here, the blue line here. So that's the decision boundary. Anything over here is red, anything over here is blue for a red versus blue type of strategy. Now, this is the difference of separation versus 1 versus all. It's either of the green class or it's anything else, or it's not. The only thing we know about it is that it's not a green. It's not green. So we're saying it either is green if it's on the right side of this green boundary, or it's not green if it's on the left side. If we look at this blue class, one versus all, it either is blue if it's on this side of the line, or all we can really say if it's on the other side is that it's not blue. It either is red or it's not red. So then you get these weird spaces where you're not really sure what type of class to try to infer those as. Okay, here's another extra resource, lots of extra resources today. Any questions on one versus one, one versus all? They're pretty straightforward with everything else we've talked about. It's just one slight extension on a different way you could transform your target. Okay. Adding on to our complexity. Machine learning is kind of like chemistry. You know, you go into chemistry 1. I might have already said this before. You go into chem 1 and they tell you these are the rules of chemistry. And this is how chemistry works. And you have all these rules that you work by. And then you go into like organic chemistry later and they say, we're going to learn about all the ways in which we break those rules. You know, they throw everything out the window. So we're not breaking rules, but we're adding on to this complexity here. So we've been talking about everything in the aspect that it is that thing or it isn't that thing. So if we look at a picture of a dog, and we want to know, is it a dog or is it a cat or is it a horse or is it a mouse? And in multi-class classification, in the way that it's defined in the domain, it has to be one of those things. But in reality, if you look at real pictures of real life and real things, you're not always going to see a picture. There's going to be a high proportion of pictures that aren't just dogs. There's a lot of other things in the pictures. There's cats and there's people and there's horses and there's trees and there's the sky and there's the ocean and maybe you want to label all of those things. So there's an extension on this. There's a complication to this called multi-label classification, not to be confused with multi-class label classification. Multi-label classification, where we want to know, is there a dog in that picture? Yes. But also, is there a cat in that picture? We're asking each question independently. Where this one's an or, we're saying dog or cat or horse or mouse in multi-label or statement across everything. In multi-class. In multi-class, we're saying or statement across everything. Dog or cat or house or mouse. In multi-label, this is we're asking each question independently. The answer to dog has no bearing on the answer to cat. So if we say, that may not exactly be true. If there's a dog in a picture, you could have a higher probability of there being a cat. But in terms of the model, the answer for dog is independent of the answer for cat. So we're saying, what is the probability there's a dog in the picture? There's 0.8. What is the probability there's a cat in the picture? 0.8. A horse in the picture. So I think it probably over-explained this, but you can check multiple of these is the answer. So in that example I gave, where we had the document that had the comments on it, and we wanted to predict who could take action on that, that's actually multi-label classification. I've been talking about it like multi-class classification to simplify it, but it's actually multi-label because HR could take action on it, and legal could take action on it, and sales could take action on it. They each might have a role that they need to play on one given comment. Blurry picture, sorry. But just summarizing. So in binary classification, you just have two labels. That's the term binary, and you got to pick one. It's either label 1 or it's label 2. And the probabilities for each sum to 1. In multi-class classification, you have to pick one, but it could be n number of labels. How many classes do you have? The probabilities still sum to 1. That's very important. So in most applications, still sum to 1. You can, if they don't sum to 1, you can weight them to where they do. So these can all sum to 1. You're going to have either a higher probability of it being a banana or an apple or an orange, and all those probabilities will sum to 1. Multi-labels do not sum to 1 in terms of probability. You can have a 0.8 of a dog and a 0.8 of a cat and a 0.8 of a horse, and that's way above 1. So they do not sum to 1, and you can pick all that are applicable, not necessarily 1. You can think of these like a bunch of different binary models. So, you can think of label 1 here as just being a binary model. Is it label 1 or is it not label 1? And you can think of this one here as being a binary label, a binary model. Is it label 2 or is it not label 2? And this one here is being a binary model. Is it label 3 or is it not label 3? So each of their probabilities don't need to sum to 1. Okay. Any questions on that? We're going to do a breakout next. All right, let's do a breakout. That's it for us today. We're just going to do this breakout. So if you download the multi-class classification one, oh, sorry, we did that one earlier. One versus all and one versus rest. So we're going to use, again, we're just going to use sklearn. We're not necessarily going to write our own methods here because that might take a minute. And so we're going to spend maybe 15 minutes working with the iris data set, which we're very familiar with at this point. So we're going to load in the iris data set. Load in the iris data set. We're going to train test split. 42, is it 42 that's the answer to everything? What was the number? I don't remember. But
Hitchhiker's Guide to the Galaxy.
Is it 42?
Yes.
Awesome. So we're going to say 42, answered everything. Binary classification. We're going to make a binary classifier. We're just doing a logistic regression. You can max it or you can increase it if you want. That's fine. We're just making a basic model here so we can just run our classifier. What you're going to do is implement 1 versus 1 classifier and 1 versus all classifier. So you can calculate those metrics. The difference of the same, it's going to be the same data set. It's iris data set, and you have the same model. So we're not changing anything. You're just going to look at the difference in the 1 versus 1 accuracy versus the 1 versus all accuracy for these. So you can look these up. I mean, I'm already in sklearn. I can probably just look it up here. There we go. Here we go. 1 versus 1. So here's the 1 versus 1 multi-class classifier here. So you can check that out. And then there's also a 1 versus rest in there as well. So you can find that. So you're going to implement this. You're going to instantiate this. So you're going to need to, you probably even have examples down here. Yep. So you're going to need to create an instance of your 1 versus 1 classifier. You're going to pass that model to it that we already created. And then you can call fit on it and pass our xtrain and our ytrain data. Then you're going to need to make a prediction on it. So for that same classifier, you're going to call predict, your classifier.predict, and then you're going to pass our test data to it. And so do that in there, and then you can calculate the accuracy. So then you're going to need to use an accuracy metric on the fit versus the predict for that. So, all right, I've talked enough. Let's spend 15 minutes on that. So, be 40, 43. Go back at 43. Okay. Does anybody have a solution they want to share for 1 versus 1? Otherwise, I can share one. Okay. Do you have one?
Do you want me to throw it in?
Throw it in the chat. Yeah.
All right, hold on a second. Let me get back to it. I don't know where I put it. There it is.
Excellent. Look at you even putting it in a code block. I love it. Makes life easier. There we go. Okay, perfect. So we're going to create a classifier, an instance of the 1 versus 1. And we're going to pass it our binary classifier, our logistic regression. So it's still going to use our logistic regression as the classifier, but it's going to apply some transformations to our target variable, to our Y train, so that it's a 1 versus 1 approach. So then we also need to fit the data. So we need to fit our X train, Y train, just like we do with any other classifier object. That's just standard sklearn structure. Now we need to make our predictions. So instead of making our predictions using our binary classifier, we've wrapped our binary classifier. You can think of this as a wrapper. We've wrapped it in a 1 versus 1 classifier. So we need to call predict on our test set. So we pass xtest to our classifier.predict function. And then we're going to calculate accuracy. We have accuracy score, and we're going to pass y-test and our preds. And that'll give us our accuracy metric for this. So we have our 1 versus 1 accuracy. We're very good. We have 100% accuracy. Now we have our 1 versus all classifier, which is going to be pretty much exactly the same. So really, really simple. We're just exact copy paste your code and then change this to 1 versus rest instead of 1 versus 1. But everything else is the same. We fit, we predict, we score, and we print that out. We can see that the accuracy is just a little bit smaller, just slight dip in accuracy in a 1 versus all model. Excuse me. All right, that is all that I have for you guys today. Thank you so much. And we'll see you tomorrow if you happen to show up tomorrow. You know what? I'm going to stop streaming so we can ask questions.